Okay, let's start the discussion. We will start with some questions. There were a lot of questions during the talk, which all could not be thrown at speakers. Now they are freely available, so you can ask questions. So we will start with the question, and there are a few topics which people have already entered on the Google document. So let's see, to start with. Any questions? I think it would be better this way rather than pushing this thing so that you can have the.
You should all be closer to them.
Let's first see. First we'll start with the questions. Then we can go over any of the topic, and if you have to make some comments. Yes. 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 Suresh, go ahead and introduce yourself and ask questions.
Hi, I am Suresh Doravari from IUCAA, part of the LIGO India team. My question was regarding the decihertz detectors to Jan. You mentioned that there are specific difficulties with decihertz detectors, which is different from the terrestrial and the LISA kind of detectors. Could you elaborate a little? One thing which Bruce pointed out and you answered was about subtraction of the environmental local noises. Are there other such things which are, because it's been almost like a 15-year effort trying to get to the bottom of this, and we seem to be having difficulties. Could you elaborate on the difficulties?
So if you, I mean, of course, there's a vast, different approaches to do that. I mean, if we start with the terrestrial detectors, so under gravity, the detectors that we are familiar with, they always have to deal with suspension thermal noise. So that's like kind of the fundamental connection here between things under gravity and making gravitational wave measurements. You need a suspension to hold against gravity. I mean, I will come to exceptions to that in a moment. So that was, I think, the suspension thermal noise is seen as like the first showstopper against any decihertz detector. And that is no matter where it is, if it's under gravity, you would have to deal with the suspension thermal noise. Now, on Earth, people came up with ideas that avoid suspension thermal noise. For example, a Japanese group has been, looking into what they call the juggling or juggled interferometer, where they throw the test masses into the air and then they interrogate essentially the positions while they are falling. And of course, similar to that is the idea of the atom interferometers, where you still have the laser that interrogates, but now it's pulse laser, so it's a bit different. But the point is that the atoms are in free fall. And then you can circumvent the suspension thermal noise. So let's say that in the last 10 years has like disappeared as a fundamental limitation, because these atom interferometers could in principle work. But then, of course, on Earth, you come back to the other problem that that there's this immense foreground of environmental noise, which really enters at this point as a fundamental limit and not anymore something that you might be able to deal with technology. And by the way, really, you can, it just gets worse, because people say like, yeah, but let's like make like, tens of thousands of sensors in the vicinity. No, what happens is if you increase the number of sensors, you increase the number of parameters of your filters, and it's just getting worse. So there's an optimum number of sensors that minimizes your statistical error. And then, it is a trade-off between statistical error and getting the information out of your data that you need. And so that optimum, unfortunately, doesn't work for decihertz. I mean, it's just not landing, not enough cancellation.
Can I ask a follow-up about your question? Because I'm interested too. So suppose you build an atomic fountain, you make something that's 5 meters high, 1/2 AT squared. If A is 9.8 meters per second squared, that means you launch something up 5 meters and it comes back down. That's 1 second. So that's a 1 hertz, right?
Basically, yeah.
And so now you've got no suspension there, right? There's just an atom flying up and back down again and falling down. And so what are are the fundamental sources of noise then just density fluctuations in the earth below? I mean, you can put this underground and far away from people. So what's the environmental noise there that you can't get rid of?
Yeah, so it turns out that the Earth is noisiest in the decihertz band, unfortunately. So it is exactly that band that has the biggest peak of environmental noise, which is really coming from the oceans. Not only, there's even, so it's the ocean waves essentially that emit most of the energy into the seismic field at decihertz. And even there is a nonlinear atmosphere-ocean interaction between the ocean waves and atmospheric pressure. And so you see that oceanic microseismic peak in the decihertz band, you see even in the pressure spectra. So it is all around. So in, essentially in the atmosphere, in the seismic fields, you have a huge peak in the decihertz band, which makes it even worse for you. So yeah, if you didn't have that peak, if the oceans were absent, then maybe you would have a shot even on Earth. But you don't.
How does that couple into the detector? Like you've launched your atom up, it's flying just in the vacuum. And
Oh, but in the end, so the way the measurements work is you need a long baseline nevertheless. And so it is not that it is a local measurement in that fountain where the gravitational waves couples, but it's like two fountains very far away from each other and a laser connecting them. And so it's very similar to LIGO, just that, that the suspended task masses are substituted by fountains, two fountains. And then, of course, they are subject to any other gravitational fluctuations as the task masses of LIGO.
Thank you.
Yeah, so I had a question in the similar lines, because whenever I see this ET curve or C sensitivity curve, it starts from 5 Hz, but the LIGO we have from 10 Hz. Like, what is making us, don't we have the technology, or why we are not able to go to 5 Hz in LIGO? Because I know that seismic noise is at 10 Hz, but in ET and CE, we are hoping to reach 5 Hz. Like, why we are not able to reach 5 Hz currently is one of the questions.
So I think I'm the only hardware person, so I'm like answering to that maybe as well. So yeah, so LIGO, of course, it depends on what you mean with LIGO. LIGO is has a built suspension system, a built seismic isolation system, and when you assume that, then it is just made for detections above 10 Hertz and not below 10 Hertz. So if you want to take the LIGO facilities and make them a sub 10 Hertz detector, you would really have to change everything, except maybe for the vacuum system. So the pipes. Now, if the question is, could you at the LIGO sites measure in principle in the future gravitational waves below 10 Hertz? It's a tough question. So again, at that point, because you could imagine to have like ET type suspensions, for example, why not? But at this point, I would again be first worried about the environmental noise and the gravitational foreground at this point, because it's a surface detector, so you would have to deal with the atmospheric gravitational noise as well as with the seismic gravitational noise. And we understand that it will accumulate essentially, between 10 and 20 Hertz at the surface already, starting to limit LIGO. I don't want to say hopefully soon. I mean, I'm saying hopefully LIGO will be limited by Newtonian noise soon, because then we will start to learn something about it. But of course, so in any case, and then you would have to subtract the Newtonian noise as well. I mean, maybe you can get below 10 Hertz, but not much, because really it's very tough. If you look at ET, I mean, ET is getting, by the way, we want to go to 3 Hertz with ET, right? That's a tremendous challenge, because you need cryogenics as well. So because again, it's a suspension thermal noise that at some point hurts you. So you have to be cryogenic. And then with ET, we believe that we can get to 3 Hertz only because we go underground. So you would have to really analyze carefully. I mean, I think the best that you can do at the surface is really what Cosmic Explorer people tell you. They have like a very clear concept, and they say they can subtract by a factor 10 essentially the gravitational noise, and then you get to Cosmic Explorer. To think that at the surface you can do better than this is, I think that's not realistic. That would really be like, you would have to come up with crazy ideas essentially that we cannot really work on at the moment.
Make a comment too. I had a comment, since this is discussion, I just wanted to make a comment for the people here who are theorists and not hardware people. A nice way to think about suspensions is the following. Imagine you have a mass hanging on a string. So here's the mass down here, here's the string, and you're holding it up there. So if you move the string slowly back and forth, the mass will just follow. It will just always be underneath your support point. And that's if you move it up here below the resonant frequency. Now, if you move it below the frequency at which the mass would swing. On the other hand, if you wiggle quickly up here, compared to the frequency at which the mass would oscillate back and forth, now the mass doesn't move very much. And in fact, you can show the transfer function between, so at low frequencies, if I move back and forth here, the displacement of the mass is the same as the displacement of my hand. But at high frequencies, if I wiggle by an amount x here, the amount that the mass moves down here falls like 1 over f squared. So for example, if the resonant frequency is 1 hertz and I'm wiggling at 100 hertz, the motion is suppressed by a factor of 10,000. And so that's the principle, that's what cuts off the response at the low frequencies. And typically the suspension has a bunch of stages, and each stage puts in another factor of 1 over f squared. So the steep, sharp curve that you see at the low frequencies is just set by the product of those transfer functions. Did I get that right? Yeah, so that's at least one way to think about that. And now moving down the low frequency cutoff in principle just means lowering the frequency of the suspension, and that works unto a certain point. And then can you explain why you can't lower it arbitrarily that way? Why can't you just make the suspension frequency lower and lower?
Yes, okay, there are different approaches that you could reduce resonance frequencies. One is you make the pendulum longer and longer. Now that is a bad idea. First of all, you need like enormous towers, fine. Maybe underground you could even do it like in a vertical shaft. But the other thing is that you introduce, there are more degrees of freedom of a pendulum. For example, one of these are the violin modes. And they will become lower and lower frequency when you make them longer, the suspensions. And so these resonances will then all show up in the comp, in your observation band. And this you don't want as well, for example. But there are other ideas. People came up with ingenious concepts to create very compact small systems with low mechanical resonances. And one, for example, is if you combine what we call spring and anti-spring dynamics, or inverted pendulum dynamics. Essentially, an inverted pendulum is when you have like a stick on the ground, and there's a cantilever attached to the ground, and so the pendulum can move like that. Now, that is an inverted pendulum, which is potentially unstable. If the flexure is not strong enough, it will flip over and never come back. Now, if the flexure has just the right stiffness, you will have like a very, very, very low frequency resonance. And it doesn't really matter how small the system is. You can design it small and still with an extremely low resonance frequencies. Then there are practical issues with that. You have to, to stabilize temperature and so on, that the geometry stays the same all the time and so on. But in any case, that is in principle how you can do it. And that's how we do it, by the way, already in Virgo. We have these inverted pendula in Virgo. In ET, the inverted pendula will also play an important role. You can do that, but there are always limits, because at some point it becomes very sensitive to temperature. There are groups, for example, in Hanover, they had like what they called geometric anti-springs implemented as part of their isolation system. And what they saw is, yeah, you can realize very low frequencies, but then that frequency becomes very sensitive to temperature, because the whole thing starts to deform when there's a little change in temperature. And then, it's a big problem. So there are always some practical issues that you end up fighting with. So I think ET, I believe, is the most ambitious and reasonable among all the ambitious low frequency projects, the only reasonable one. For terrestrial detector.
Hi, I'm Sumanta from IACS. So my question is, in this session, we all heard about low frequency detectors like hertz, decihertz, millihertz, nanohertz. But what about high frequency gravitational wave detectors? I mean, are there any interest in them, or there are some active?
So I have a couple comments about this. So first of all, in standard slow roll inflation models at the gut scale, you generate a stochastic background up to frequencies of gigahertz. So, And in fact, there are other sources of very high frequency gravitational waves. For example, if a neutral scalar particle, for example, decays into two photons, two massless particles, for example, that generates through the memory effect also a very small amplitude, high frequency gravitational wave. So there are sources of high frequency gravitational waves, but sort of not from in-spiral systems, not from that kind of thing. Now, people have contemplated building high frequency detectors in the megahertz range, and there is work ongoing on this, but there's nothing that's nearly sensitive enough yet to detect the kinds of sources like I'm describing. So yes, it's possible in theory. In practice, the levels of sensitivity that have been achieved are just nowhere near close enough, nowhere near good enough.
I can quickly add to that. So there are tabletop detectors that try to do this. So one of the groups that come to my mind just off the top of my head would be the Cardiff group that has atom interferometer detectors, but which is purely for this science case. But as Bruce said, the sensitivity is nowhere close. So all you can do right now is what we used to, I guess, do with gravitational wave detectors back in early 2000s, which is you place upper limits, right? And yeah, but
the ratio of sensitivities is much worse than we had.
Much worse. 1980s, I guess. But no, you place
you have to
upper
go back
limits.
even further.
I see. But yeah, there are initiatives, but I don't think anywhere close to realistically picking up something.
By the way, the future of gravitational wave detectors is rather simple. If you go forward 200 years from now, gravitational wave detection will be an undergraduate experiment that you do in a lab course. And it's going to be based on precision clocks. We don't have clocks yet that are precise enough, but imagine one day when you have a clock that measures time to a precision of a part in 10 to the 24. In that case, you can detect gravitational waves. This is the same as, to measure the speed of light. This was done in France first several hundred years ago, and it was very complicated. Now, you go into an undergraduate lab, you take a dual channel oscilloscope, you plug in, two cables, one of which is 5 meters longer than the other, and you can see the phase shift between the two signals. So you can see the propagation time in a longer cable in 5 minutes in the laboratory with equipment that you can buy for 400 euros. So in a couple hundred years, I mean, there will be techniques for detecting gravitational waves in a broader range of frequencies, which are very simple. We're just not there yet.
This is maybe a question coming from someone who's not very experienced with instrumentation. So when I look at the noise curves, as I go from, can you hear me?
Yes.
Okay. So if I look at these noise curves, these sensitivity curves, as I go from lower frequency to higher frequency, starting with LISA, then DECIGO, and then the LIGO detectors. And if I look at the bottom of the curve, I find that the bottom of the curve gets better, it gets lower, the higher I go in frequency. Is there a way to understand that? Why is it that we can push the noise floor more down the higher we go in frequency?
Well, okay, you might get different answers here. One answer is just that the energy density is proportional to H dot squared. It's like electric field squared. H is a potential. Take the time derivative to get a field and square that to get a density. So it's F squared H squared. So if you keep it a constant energy density, that means that at higher frequencies, larger F, you have a smaller H. That's one way of thinking about it.
Yeah, to add one thought, if you look at the LIGO, if you ever saw the LIGO noise budget, then you will see that it is quite easy to understand at high frequencies if you are into instrument science. But even the best instrument scientists don't. I think that one. No? Yeah, okay. But the low frequency spectrum is very hard to understand. For two reasons, it's difficult to model any noise at low frequencies. In addition, there are many, many, many noises that tend to rise at low frequencies, electronics noises, thermal noises. There are so many noises that go up at low frequencies. And so that is another reason you simply cannot make any part of the instrument work as well at 1 hertz as you can do it at 100 hertz. So this is just another aspect of it.
But were you asking about sort of at the bottom of the dip?
Yes,
the
exactly.
relative height? If you plot it in terms of omega, energy density, not in terms of strain H, then for example, today LIGO has a sensitivity of omega that's around 10 to the minus 9 or 10 to the minus 10. So do the PTAs. It's almost exactly the same number. So if you go to energy instead of strain, then you see that they're very similar.
I showed that plot. It's a similar across the band. LISA, LIGO, SKA, and all.
Yes, Gopu, you surprised us. So you have a hand raise. So are there a comment question? What is it?
Oh, I'm sorry, I've been raising my hand for a while. I think you were busy. Yeah. Okay, just a follow-up of that. Maybe I will. Okay, so this is about the LISA talk about possible constraints on the extreme mass ratio in spiral rate. You already have QPEs, right? This X-ray bus these days, and they have been proposed possibly because of the stellar mass black hole passing through the accretion disk and all that. So that can put you kind of constraints on MRAs. Are they reasonable?
Are you asking about constraints on the rates or constraints
on? Based on QPE's existence.
If you believe the model for QPEs, yes, you can put constraints. Also TDEs, you can use TDEs as to inform the astrophysical models, and this is partly what we do. Yeah, we don't do it for. I didn't do it for QPEs, but for tidal disruption events. Yes.
Thank you.
Yeah, I mean, we have a paper which is coming out on this, so you still get a large uncertainty because the data on TD, I'm talking about TDs here, QPEs, I didn't do the analysis, but for TDs, there are a number of uncertainties in the data, so you can still fit the observations with many of those models that I showed in that table. For QPEs, the quasi-periodic eruptions, there are many models, and they're not necessarily precursors to MRIs, as far as I understand, because they could be blobs in the disk, they could be so they're not necessarily.
If I could ask a related question on the global fit problem for LISA, how certain are we that it is going to hit us? Or are the rates so uncertain that we will know only when we turn on LISA that there is
I didn't understand the question. I didn't understand the question about, are we sure we can do the global fit?
Or no, will there be a problem in the sense that there will be too many? Overwhelmed with the number of overlapping signals.
But we already know that there are too many. Some of them will be unresolved. If there are too many, they will just contribute to the you're talking about MRIs here? Or,
no, I'm talking about the whole spectrum.
Sources. For white dwarfs, I think we have a good idea of how many there are, and there are also prototypes of the global fit that are shown to work. For massive black holes, if there are really thousands of them, I mean, we hit a problem with the waveforms, because when you subtract one of these sources, it could leave residuals. But yeah, if we are of the order of 100 sources, that shouldn't pose a problem. This is what we do in the LISA data challenge. For MRIs, I don't think MRIs can pose a problem for other sources, but you could miss MRIs, or you could misrepresent the physics behind MRIs, or you could mistake an MRI for showing violations of GR, while instead it's simply something more mundane. But I don't think,
Thanks.
In your talk, at the end, you showed this idea of doing population inference for white dwarf binaries without doing a global fit. And so one way to think about this is if you're going to do a global fit for, let's say, thousands of white dwarf binaries, each one has many parameters that describe it, like its location on the sky and its orbital frequency and things like that. So then the global fit is a fit for thousands of parameters, whereas the population inference, for example, is just things like how are they distributing the bulbs. That's just a handful of parameters, much smaller number. So that's kind of why it works, right? Because you're not trying to get all these very large number of parameters. You're just trying to get a few. And you can do that, as you showed, easily. But does that help you, though, with actually finding the gravitational wave signals? Or if you want to find the gravitational wave signals, you have to go back and do the global
I think
fit?
it does, because it does. It gives
That's what I didn't understand.
Yeah, I think it does, because ideally in the global fit, you would like to do a hierarchical analysis. So your priors wouldn't be flat, but they would come from an astrophysical model. So not working. There is a threshold detector. You have to speak a little bit louder. Yeah, so I think it does help you, because you can use that as proposal for an MCMC, because the global fit would include the hypermodel as a prior. So you would
gives you the prior.
This gives you the prior. Also, the global fit is intrinsically iterative. So
I was a bit wondering.
The question online, Mukil Chandra Kumar, you had a question? Or?
Yeah. Actually, I had a question for Ish. So you had showed that plot with the 10 solar mass peak, right? So in that, there was a peak around the 30-40 solar mass. So is that indicative of anything, or is it simply like an effect after effect?
No, it's indicative of something. And the
Yeah,
problem is it could be indicative of many things. So there are proposals about it being indicative of a sort of a PP-ISN gap. So the fact that beyond a certain mass, you have a pair instability supernovae. So stars basically go supernovae instead of actually collapsing to a black hole. And just before that, you get a peak. So if the pair instability supernova began, let's say at 50 solar masses, you'd maybe get sort of a pulsation pair instability peak around 35. So it could be that. It could also be that there are stars, or rather black holes, that are formed due to chemically homogeneous evolution of stars in a binary. So even that can give you some sort of a peak near 35 solar masses. It could also simply come from hierarchical mergers, if you will. Around that point, you could have stable mass transfer episodes. So the problem is that right now we don't know necessarily what that peak really corresponds to. There is actually a recent-ish paper by Soumendra and Wilfar et al. And it's basically on this problem. And if you go down well enough in that paper, there's a table where they mention all the different formation scenarios that could contribute to the peak. And where do they, so let's say you chose chemically homogeneous evolution, while it can contribute to the peak of 35 solar mass, it also gives you some features and spins, let's say. And are those features still consistent with what you're able to observe? Right, so it summarizes things in a very nice table. So yeah, it definitely means something. It's statistically significant. We don't know what exactly it means right now.
Yeah, okay. And also, like, I mean, I had written this in the Word document, but I'll ask here itself. So, like, you had told, like, the MBHBs, so if they don't merge, they form triples. But in the case of triples, the Kozalero time scale is very large if they're very massive. And even if they even if they reach those large eccentricities, then again they circularize again, and again the final parsec problem would come into picture again, wouldn't it?
sorry, I'm not sure I understood the question.
Okay. So, like I'm saying, so suppose you said that the MBHBs would form triples in the case they don't merge. So these would take, like, the Kozai-Ledau time scale would be large for such high masses, and their even if they reach those high eccentricities, after that they'll again circularize. Then again the final parsec problem comes into the picture, right?
No, but yeah, they don't circularize. That's the thing. I mean, the eccentricity is so large that it remains significant when they enter the Lisa band. So that's because the eccentricity can be larger than 0.99, so they don't circularize.
Okay.
In fact, even when they merge, they have a residual eccentricity of more than 0.1.
Oh, okay.
The calculation, if you do a simulation for typical parameters of the system.
Okay.
I had one question in the decihertz band. In decihertz band, you have this lot of continuous gravitational waves also will be coming, and also you'll have long in spirals. So how you will manage this overlapping signals? Is there a better way to extract each of them in a clear way, or if the signals overlap, will we end up biasing the parameter estimation or even the search itself?
So I think the situation in the decihertz band is more similar to what we have also in next generation terrestrial detectors, that there are many, many signals and they overlap in time, but they don't interfere much in parameter space, if you want. That means you can actually disentangle them. And I mean, you might have to, because as you know, if you want, the background formed by all not yet detected binaries might bias your parameter estimation. So you might have to do two steps. So you might have to do first detect them biased by the background. At some point they are all kind of detected, and then you refine the parameter estimation of all these signals in a second step. I think we have not yet come up with a concrete way to do it, but this is kind of maybe one of the ideas how you could be able to do it. And I think that, and this is what we also proposed for Big Bang Observer when we initially looked into the foreground subtraction, essentially to do a hierarchical, and you never get to the global fit kind of situation in these bands. So you would always be, you're better off in these cases to just do hierarchical parameter estimation if you want detection.
I have a comment to make. When you think about overlapping signals, overlapping in time, a good way to think about it is think about making a time frequency plot. And then you'll see that even though the signals are overlapping in time, in the time frequency plot, for example, the chirps are actually quite distinct from one another. So imagine that there were music playing here in the background with a woman singing, higher frequency voice than mine. You'd have absolutely no trouble distinguishing them, even though they were completely overlapping in time. So think about overlap, not in terms of overlapping in time, but in time frequency.
Hi, this is. I have one question to Enrico. Can you hear me? Yeah. So there are increasing number of papers about, let's say, this any additional field coupled to gravity, like scalar field and etc. So what do you think about what kind of unique prospect the LISA will bring to that?
Yeah, they're very fine-tuned in a sense. I mean, yeah, in some cases, in some specific cases, you may be able to see them, but yeah, you need typically in these theories, you need coupling constants which are of the same size as the size of your physical systems. For instance, with LIGO, we can test coupling constants of order kilometers. With LISA, we can test coupling constants which are even larger. So if you believe your modification of gravity comes from the UV, you're going in the wrong direction by going to LISA. If you're trying to probe theories of cosmologically motivated, then maybe your game. But still, the energies that you have are very far from the energies at which you, both from cosmology on the one side and from UV from the Planck scale on the other side. So yes, you can constrain them in some specific cases. But yeah.
Hi, this is Debojyoti from Raghunathpur College. So I was just wondering about the first discussion by Professor Allen, in which we saw one curve where we saw the maximum ellipticity possible for a neutron star. So I was just wondering that how do we comment on such maximum ellipticity? Does it come from some Keplerian limit of the rotation? And I just have a small follow-up question regarding that. When we talk about the continuous gravitational wave emitting from such neutron star, at the current scenario of the instruments, the detectors that we have, if there is some unique phase transition or something happening which gets reflected in that continuous gravitational wave, do we indirectly somehow may be able to detect that? I know directly it is not possible for continuous emission wave to detect.
Let me say something about the first question, okay? And then, by the way, who's the person speaking? Okay, I'm sorry, thank you. My eyes aren't very good. I'm going to I'm going to say something about the first part, but then ask me the second part again, okay? Because I'm not sure I understood it. So those limits on ellipticity, they're just limits, right? They're not an observation. They're just saying that if there were neutron stars out there at the galactic center distance with an ellipticity above 10 to the minus 6 and spinning at 700 hertz, then we likely would have seen these. So those are just limits. And as I said, the ellipticity of 10 to the minus 6, that corresponds to mountains which are about a centimeter high on a neutron star, or deformations. Now, if you look at the best limits on the eccentricity from known neutron stars, the best limits are around 10 to the minus 8 for some isolated recycled neutron stars, which is amazing, right? That means that the mountains, or the deformation, it's not even a millimeter, it's 100 microns. So it's absolutely fantastic. But we don't have any idea what that ellipticity ought to be. We don't know enough about neutron star structure, and we don't know enough about the conditions under which they formed. So there are some lower limits, but they're very, very low. But we already know that some neutron stars are incredibly round. I don't think you can manufacture in a laboratory. If you take the very best bearing ball that you can buy, a 25 millimeter diameter hardened steel ground ball, which is as perfect as you can make it, I don't think it's precise at 10 to the minus 8 yet, because that's almost getting down to nanometer precision on the surface. So neutron stars are already incredibly round. So first part of the question, we just don't know how big the deformations will be. Okay, what was the second part of the question?
Thanks a lot. And secondly, I was just wondering, for such standalone systems where we get continuous waves. So at the current state, I know it is not possible to detect those, but I was just wondering if maybe if there is some phase transition signature that gets reflected in that continuous wave, do we somehow indirectly maybe able to detect such things at the current level?
I'm not sure what you mean by phase transition
No,
signature.
I mean if some funny business is happening in the neutron star where the star gets either spinning faster or slower.
Oh, like glitches and so on.
Yeah, maybe. Yeah.
Oh yeah, in fact, these are a complication right now in the search. So it's known that neutron stars glitch. That is, their regular rotation is suddenly interrupted, and they change frequency and spin rate and then relax back. And this is thought to be due, for example, to recombination of magnetic flux tubes, for example, in the interior of the star, things like that. I think people have searched for transients coming from neutron stars sort of at the time of the glitch. The trouble is that radio astronomers can typically tell you, a glitch happened sometime during this 2 weeks. They can't tell you the moment that it happened. So those kinds of searches, people do those kinds of searches, but nothing's been found. Certainly something to look for. Does that answer your question, or am I missing the point still? Okay.
Okay, let's go online. Gopu, you have a question or a comment?
Yes, and a follow-up on that Kosai, argument put forward, high eccentricity, but I remember that the simulation included post-Newtonian equations, but if there are spins, so involved, the precision actually will interfere with the Kosai resonances that can actually drive down the resonances. This has been already pointed out, even binary pulsars, which are supposed to be circular, are eccentric and all that. So is that being looked into?
No, you're right. In that simulation, we had all PN terms, three-body PN terms, so three-body interactions up to 2 PN, but with no spins. Because is the Hamiltonian of a three-body system known, including spins? I'm not even sure.
Not really, but you can actually ignore that fact and just look at the inner binary spinning, because this will not couple
we could add
to the higher.
two-body spin interactions.
Yeah, and then you can look the octopole contribution, non-spinning. It doesn't really matter. I don't think it's going to change dramatically.
I think it would be subleading, because the spin-orbit interaction would be 1.5 PN, right?
Correct. So that will be interior. Exactly.
Already 1 PN makes Kosai lead of less efficient, right? Because
that's
of
right.
the Astron
That's
precession.
well documented by Rossio.
That's a good point. But I think it would be less important than 1 p.m. But yeah, it should be checked.
Yeah, thank you.
Okay, go ahead.
Can you hear me? Yes. So hi, I'm Kaushik. I'm a postdoc at ICTS. So my question is regarding LISA data analysis. So I was wondering if, since LISA will be detecting, I mean, huge amount of data, right? The duration would be very much, right? So can we do this? Can we divide the data in chunks and use a simple Taylor PN waveforms? Of course, you have to include eccentricity because LISA, I mean, will of course detect the very early in spiral cycles. So eccentricity is a must. Can we do that? Like use a simple Taylor frequency domain waveform and analyze the early in spiral part, and maybe it will, I don't know, I mean, it will expedite the data analysis process.
Yeah, I don't think it's really needed for the loud sources, the supermassive black hole sources. But yeah, this is, I mean, splitting the data in chunks is something that we do for white dwarfs, for instance. But we don't split in time, we split in frequency. Or you could try to come up with consistency tests. So not necessarily with, so you mentioned Taylor, I mean, not with those simple models, but for instance, you could try to see if there is an effect of the environment by analyzing different chunks of an memory. So first 1 year, then 2 years, and see if the posteriors shift, if there is a bias. This is something that we're trying. But yeah, for the what you're describing about fitting the early in spiral is something that might find an application for low latency. So you could use a simple waveform model to try to. Say it again. Yeah,
merging during the observation.
Okay, yeah, the systems are, I mean, all these systems are merging. So you won't, if you just fit in spiral, you would lose most of the SNR. In fact, this is the challenge of low latency, to infer the merger time and sky position with just the beginning of the signal.
Hi, this is Rahul from IIT Bombay. I have two unrelated questions related to detector design. So one is about binary neutron star mergers. So we did quite a number of simulations leading to phase transition in the post-merger signal, as well as identifying them as prompt or delayed collapse of neutron stars. And these post-merger signals can be detected if you can tune the detector at high frequencies, having low PhDs, and that can be done even for, we are going to have a network of detectors. So what we can do, we can choose one detector to have tuned to this high frequency range, and others tuned to the in spiral. And then that will allow us to also capture this post merger, because that is going to give us the information about hot, dense nuclear matter, which as opposed to the cold nuclear matter, which is the in spiral. So what are the prospects of that? So that is one question. The other question is about binary white dwarfs. I was really happy to see that binary white dwarfs are playing good role, because we have done many simulations leading to type 1a and all. But when I see the LISA sensitivity curve, it's ramping up where the 0.1 hertz around is just below that, and decihertz is going down. So the right in the range, 0.01 to 0.1 hertz, nothing has their best sensitivity in that range, where white dwarfs are going to merge actually. So is it like we are not focusing on them, and it's like we are all trying to avoid them? It's like a nuisance. That's my feeling. So these two comments. Thanks.
I can answer the first question. So for Cosmic Explorer, at least, there's definitely the idea to have the 20-kilometer Cosmic Explorer detector that can be post-merger tuned. So what that would mean is that the usual dip that we get of around, 500 hertz-ish, now you also find a dip that is beyond 2 to 3 kilohertz or so, and which is the region that you're mostly interested in when you're talking about post-merger, right? And so the idea is that your 20-kilometer Cosmic Explorer can be optimized, whereas your 40-kilometer one still remains your wide band thing. And so the sensitivity curves that you get often are the usual and the post-merger optimized sensitivity curve for Cosmic Explorer 20. Even for ET, I guess the idea is that the band is still lower at high frequencies as well compared to what we have right now. And maybe, Jan, you can say more about it, but at least from what I remember from the xylophone designs, you had parallel low frequency and high frequency things running together. So yeah, so even there, I guess the idea is that you can probe the high frequency regime specifically.
Hello, hello. Works. Yes, if I can add to the white dwarf question. So it's not that LISA is trying to avoid it. I think they would like to see even more, even though they're already seeing so many. But the point is that LISA is not easy to make better at high frequencies because it is so long, of course on purpose, but so long that it starts to lose gravitational wave response at high frequencies.
I have a question which is very relevant to this. I know, for example, the merger rate of neutron star binaries in our galaxy is about 1 every 10,000 years, roughly. What's the merger rate of white dwarf binaries in our galaxy?
I mean, I think it is as lousy as the core collapse or something similar to it. I think, I mean, if you connect it strictly to supernova type 1a, then, then you get your rate, which is like very low, I think. Yeah, something like that, yeah.
So if I understood part of your question, it was why aren't we focusing detectors so that we can see white dwarf mergers? But the answer seems to be that they don't happen often enough.
Yeah, okay.
The rates are one per 100 per galaxies. And those are the only ones when you assume they are produced type 1a.
Can you see them in other
But if you go to other kind of transients, which is quite a lot.
But this is exactly the point that I also made in one of my slides, that even if you can just see out tens of megaparsec, it's already enough to see mergers happening per year. Several and maybe even many more. It then depends very, very sensitively on the masses of the white dwarfs and the distribution. We know, of course, a lot from our own galaxy, but is that the same story in all the galaxies? And, so it's a, but yeah, I think even if you get to the not yet so great sensitivity that LGBA will have in the decihertz band, you will already see mergers and possibly connections to supernova type 1a.
An interesting question here is what could we learn? I mean, white dwarf stars are rather well understood, right? You can find evolutionary codes that, you tell me exactly what the mix of elements is, and you can predict the evolution with incredible precision. So for example, for neutron stars, we don't know about their equation of state. And learning about that through neutron star mergers would be very interesting. An interesting question is, suppose we could observe white dwarf mergers, we had a detector tuned at the right frequency and so on, what would we learn?
So
That's
Bruce,
an interesting question.
calibrating type 1a supernova would be one sign.
Can you explain a bit more what you mean by that? Because I don't know very much about this.
If you can hit a different distance measure to a white dwarf merger producing a type 1a supernova, you're having an independent calibration to the cosmic distance ladder.
Let me
at 10 megaparsecs. Okay.
Let me also say that, I mean, I think the whole progenitor model for supernova type 1a is very complicated. For example, when the merger happens, the theories predict that the electromagnetic emission could come immediately or in million years, depending on what happens exactly after the merger and how the thing settles. It is like a very open kind of topic when you connect it to the electromagnetic world. I think from the gravitational wave side alone, I'm not sure how interested it is, but with the supernova type 1a, there's so many question marks that it will be very interesting. So in fact, the expectation is we should not expect that a white dwarf merger is accompanied by a supernova type 1a, because it could really happen so far out in time that we will never be able to make the connection. In any case, so there are some really interesting questions when it comes to that.
So I'll add to one thing. So the common thing between neutron star binaries and white dwarf binaries and binary black hole binaries is also to understand binary stellar evolution, right? And that is as poorly understood for white dwarf binaries as for neutron star, because most of the common envelope evolution, for example, and other magnetic braking, other types of processes that causes the angular momentum evolution in the binary is similarly poorly understood, and the theoretical models are orders of 2 to 3 orders of magnitude different. So I think that is a good learning.
I see. So you mean isolated white dwarfs are well understood, but when you put them in binaries, that's not so well
That's not
understood. I see.
Yeah, Patrick.
May I?
My audible? Yeah, this is Patrick Dasgupta, associated with ICSP. This is coming back to the ellipticity of neutron stars. So one would expect the magnetars, where the magnetic field is very high, one would expect that the magnetic deformation would cause relatively larger ellipticity in the case of magnetars. So shouldn't one be observing continuous gravitational waves from the SGR, soft gamma repeaters, which are associated with magnetars? That would be a likely candidate where the ellipticity is expected to be higher.
So where's the person asking the
Yeah,
question? Okay, thank you.
yeah.
So I can tell you that targeted searches for gravitational waves have been carried out for every single known pulsar where the emission frequency, twice the rotation frequency, would lie in the LIGO band. And indeed, if you look at models for deformation, strong magnetic fields, as in magnetars, are one potential mechanism for generating mountains on neutron stars, or for mountains, for deforming them slightly. And so that's certainly a search target, absolutely. But so far nothing's been found. And the fact that these all sky searches for unknown sources can already place limits of 10 to the -6 at distances of the galactic center, that's a bit discouraging. Now that's at high frequencies, not at low frequencies. Do you want to make a comment?
Okay.
All the magnet has been at spin frequency is less than 1 hertz. So that's the problem with LIGO and Virgo, we can't see them.
Yeah, so the spin frequency is just too low of all the known magnetars.
Way too low.
They're slow pulsars.
Okay, thank you all. We had a very exciting discussion session. Let's thank all the speakers as well as the panelists contributed to the discussion.